Hey guys, let's discuss another problem from the 2025 British Informatics Olympiad. Today we'll be discussing Frosty Relations, or FROST for short. So, as usual, I'll explain it on a whiteboard, but this is the problem statement. Check the description if you want to read this, or at the end if you want to read my code as well. So let's switch to the whiteboard. So in this problem, you're given two binary strings. So in this example, I've got two binary strings here of length 4. Binaries are composed of zeros and ones. And we have to transform the first one into the second one in a series of operations. And the operation we're allowed to perform is to choose some prefix. So some prefix of this binary string and to reverse it. So in this case, if we chose the prefix of length 1, that would do nothing because that's just a 0, so reversing the 0 does nothing. A prefix of length 2 would reverse the 0, 1 to a 1, 0, and the string would become 1, 0, 0, 1. A prefix of length 3, again, wouldn't change anything because 0, 1, 0 reversed is still 0, 1, 0. And reversing the whole string as a prefix is an option as well, and that would give you 1, 0, 1, 0. So those are the options we can do. Those are the moves we can perform. And we can apply this move repeatedly. So this operation we can apply up to n-1 times. So if n is the length of the string, here n equals 4 in this example. In this example, n equals 4. We can apply n-1 iterations of this operation at most. And we need to do this. We need to convert the starting string to the target string. So in this example, we can reverse the prefix of size 2 to give us 1, 0, 0, 1. And then we can reverse the prefix of size 3 to give us 0, 0, 1, 1. So that's the solution for this one, or a solution. That uses 2 reversals. Since n is 4, we're allowed up to 3 reversals, so all good. So how do we solve this problem? Let's dive straight into the solution. So this is the solution that I came up with. There are other solutions to this as well. So this is an interesting problem. It has quite a few solutions with some different complexities as well. The complexity they were looking for in this problem, indicated by the constraints, since the length of the string is up to 5,000, something like n squared, something like O of n squared is fine. But using some data structures, apparently, it is possible to do it faster in n log n. I'm told. I haven't explored that. But there are a couple different n squared solutions. This is not the intended one, but I like it because this one has a nice, neat proof that it works. So I'm going to show you this one. So let's get into it. First thing to notice is that since we're reversing prefixes of the string, it's a convenient thing to do to start building up the string from the end, from the back, from the rightmost end. Because in this problem, we're trying to get from one string to another, and one way of doing that is by sort of building up progress, right? We can start building up the string. But we can't really build it up from the start because we keep reversing the prefix, so we'll keep messing with the string. But if we have some suffix of the string already fixed, then we can just leave it. So in this example that we have here, for example, the 1 at the end is already matching with the last character in the starting string matches the last character in the target string. So we can just leave it and pretend it doesn't exist because it won't affect the prefix reversals on the rest of the string, because the rest of the string is a prefix of the whole string. So if we just solve the rest of the string, then we'll be done. So yeah, the first observation is build the string up from the rightmost end. So let's do that. So what do we run into here? So we start thinking, let's say we have two strings here. If they end with the same thing, then that's fine. We just move on to the next character. So we just keep moving left from let's say this is the right end. We just keep moving left until we find a difference between them. Right? Let's say they differ here. So now we need to somehow get these to be the same. So since we have n-1 operations in total, that's operation. Since we have n-1 operations to perform in total, it's going to be approximately one operation per character that we're doing here. So, can we get these two to be equal in one operation? Well, let's say this is the start of the string over here. And at the start, we have a 0 here. So if these two are different, it's still okay if this 0 is the start. So because we can reverse this whole prefix up to this character that's wrong. And so this 0 will end up in this 1's place. And if we need a 0 here, then it's all good. So if the starting and target string don't match, then as long as the start of the starting string is different from its current value, then we can just reverse this prefix and it'll flip this value to a 0, and we're good. And this, if we always have moves like this that we can perform, then we're good, because we'll perform one move per index, and then when we get to the end, we won't need to perform a move for the first index, because if there's only one character left, it must be matching, and so we'll have performed n-1 moves. And so that's good. The issue is this might not always be the case, right? But so this is one of the cases where we can perform this move and it works. So what if this isn't the case? What if we can't simply perform one reversal to get the current last digits to match, right? Well, that means we need two reversals at least. But if we need two reversals, then we need to get the last two digits to match, because otherwise we'll be behind, right? If we use two reversals to get one digit to match, then we'll end up using too many reversals in the long run if we keep doing that. We'll end up using more than n-1. So if we're using two reversals, we should get two digits done. As long as the number of reversals we're using is always at most the number of digits that we're getting matched up at the suffix, then we're fine. So can we use two reversals for two digits, or three for three, or so on? Well, it turns out that we can. We can always do one of them, at least one of them, which is pretty cool. So let me explain what I mean. For that, let me write out a larger example. So let's say, this is a line, and to the right of this line, we've already matched up a bunch of values. So let's say a 1 matches a 0, a 1 matches a 0, and so on. So to the right of this line, everything's good. So that's why I'm drawing it dotted, because we're basically ignoring it. It doesn't exist anymore. We're just solving the rest of the string. And now I'm just copying from an example I've drawn earlier. So, let's say we have something that doesn't match here. So again, if it matches, we just shift this line over here and just move on. But the last characters don't match. So now let's try and fix that. So if we had, like we said, if we had a 1 here, then we could just flip this prefix. This would be a 1 now, and then we'd move on. Let's say we don't have a 1 here. Let's say we have a 0 at the start of the string. Let's move the start over to give us more space. So let's say we have a 0 here. Well, let's do something like this. Let's find a prefix of the current string whose contents matches the contents of some suffix of the current target string, of the target string. So let's say, let's say we've got something like this. Well, actually here a smaller one would match as well. Let me improve this example slightly. There we go. So if we find this, and we don't care about the rest of the characters, the rest of the digits in these strings. So we found a prefix here of the current string that matches a suffix of the target string in contents. And by contents, I mean, it has the same number of zeros and the same number of ones in it. So here we have 3 zeros and 3 ones in both of these. So like the number of zeros in this one is the same as the number of zeros in this one, and the number of ones in this one is the same as the number of ones in this one. So let's say this prefix matches this suffix in contents. Well, according to what we said earlier on, remember how we said that if we get the last 3 characters to match, for example, in the prefix and the suffix in 3 moves, up to 3 moves, that's fine. So let's try and get, in this case, the suffix is 6 long. So let's try and get these 6 characters to the end in up to 6 moves. So let's try and get these 6 characters here. And let's do that. Let's restrict ourselves to only use the 6 characters at the front here. So we'll get these 6 characters to somehow match these 6 in the prefix so that we can then reverse the whole thing and get these 6 to the end, and then they'll match the suffix, if that makes sense. So if we were to copy this target suffix over to the front reversed, it would be, if I start from the end, right? Start with the 1, 0, 1, 1, 0, 0. So I've reversed this thing, this target suffix. Well, now, if we somehow get this as a prefix of our current string, then if we reverse the whole thing, this will, reverse back and it will match the suffix of the target string. So since there are 6 digits in this, we need to get this whole thing in position at the end of the string within 6 moves. So we have 6 minus 1 moves, because we need that 1 move to reverse the whole thing. We have 6 minus 1, so 5 moves to get this string as a prefix of the current string, so that we can then perform the reversal. But we've already said that this prefix, of the current prefix that's the same length 6, matches this target substring in contents. It's got the same digits, just in a different order. So they're anagrams, right? That means that the problem that's now left, if we can solve it, is to take these 6 digits and transform them into these 6, using prefix reversals in 5 moves. Now, what's that? That's an instance of the problem that we're already solving. We have to do this we have a, the problem that we have is to take a string of length n and convert it to a different string of length n in n minus 1 moves. And this is exactly an instance of that problem. We have 6 into 6 using at most 5 moves. So we have a smaller instance of this problem, and assuming we can solve it for smaller instances, now we can solve it for the larger instance. Because we'll do this. So let's assume that we have a way to solve this for smaller instances. Then we'll solve it for this 6 in 5 moves. Then we'll reverse the whole thing so that this is at the end. And now all that's left is solving the rest of the string. So whatever is here in red, it won't be touched the first 5 moves. And then in the last reversal, it'll end up reversed here. And then we have to match that up with whatever's here in the target string. So now we're left with a smaller version of the same problem. So if we find a prefix of the current string that matches, that is an anagram of a suffix of the target string, then that essentially reduces us to the same problem of converting this prefix into the reversed version of that suffix. And then once we've done that, we perform one extra reversal, and then we have the same problem again with the remaining string. So we've made the problem smaller. So if a prefix that's an anagram of the suffix exists, then we're good. So now let's just prove that always exists, and we've solved the problem. That means we can solve it recursively. Right? So why does this always exist? My claim is that there will always exist a prefix of the current string that's an anagram of the suffix of the target string, as long as these last 2 characters don't match. And so now let's see why. So let's assume one of those doesn't exist, right? So what's the problem we're in now? We have 2 strings. We have 2 strings, and the whole thing must be an anagram of each other, right? The whole starting string must be an anagram of the target string. And so now let's assume that no prefix of one matches a suffix of the other. No prefix of the first one matches a suffix of the second one. That obviously means that the first characters must differ. So one of them is a 0, the other one's a 1. Because otherwise we'd have the prefix of size 1 matching the suffix of size 1, right? So, the first characters differ here. And then we keep going. Let's say this one's another 0. This one's a 0 as well. Still no matching prefix. This one's a 0 again. If we made this one a 1, now we'd have a matching prefix of size 3. So we can't. It has to keep going with 0. and so on, right? And again, we're assuming here, we're proving by assuming the opposite. So we're assuming that no prefix exists that's an anagram of a suffix, well, except for the whole string, because technically the whole string is a prefix, and the whole string is a suffix, and we know that the two strings are anagrams. But let's ignore that. So we're looking for something else, because that wouldn't be simplifying the problem to a smaller version of the problem if we said, we can solve the problem by solving the problem. We have to actually have a smaller problem that we're solving that helps us solve the problem. So we want to find a prefix that's smaller than the whole string, that matches a suffix that's smaller than the whole string. So again, we're assuming that this doesn't exist. So that means whatever value this prefix started with, so in this case it's a 0 that the prefix started with and the suffix started with a 1. Whatever the value is that the prefix started with, it will always be ahead in that value. What do I mean by that? I mean, so in the prefix of size 1 and suffix of size 1, the prefix has more zeros than the suffix. And the suffix, if we start, adding one character each to both at the same time, the suffix will never catch up in the number of zeros it has. See, now, once we've added a character, the prefix has 2 zeros and the suffix has 1 0. But the suffix can never catch up in the number of zeros it has, because if it does catch up, then because the two strings are of the same length, they must be anagrams. So the suffix can never catch up in the number of zeros it has, which means the prefix must be ahead for the whole thing based on our assumption, because we never have a prefix that's an anagram of a suffix. The prefix must be ahead for the whole thing. But what we do know is at the end, the two strings are anagrams, right? So at the end, the number of zeros is the same in the two strings. But at the start, we know that the prefix has more zeros than the suffix, and it stays that way until the end, because we don't see any prefix-suffix anagrams before then. So that means at the end, the suffix must catch up in the number of zeros. That last digit must make it catch up, which means, the difference, it needs to close the gap in the number of zeros. So it needs to have a 0, and the prefix needs to have a 1 so that it catches up. Because otherwise, if they both have the same digit, then the difference would stay the same. And if it didn't have a 0 and the other one had a 0, then it would fall even further behind. So it needs to have a 0 and the prefix needs to have a 1. So what have we said? We've said that if the prefix starts with a 0 and the suffix, must start with the opposite digit, a 1, then if we don't see any of these prefixes that aren't the whole string, that are anagrams of suffixes, then the last digit of the prefix must be the opposite of its first, so it must be a 1 in the case of this 0, and the first digit of the suffix must be the opposite of its last, so a 0 in the case of a 1. So since these two were different, these two must be the same, and these two must be the same. So the critical thing here is that we've now deduced that these two digits here must be the same. So this 1 and this 1 are the same, which means that, there was nothing to look for in the first place. The last digits are the same. We should have been ignoring this digit. So what we've proved here, this can be made very rigorous, is that if the last character doesn't match between these two strings, then one of these smaller prefixes that matches a suffix in contents will always exist. So we just have to find one, solve it recursively using the same solution, reverse it to match the suffix, and then solve recursively again on the remaining part of the string. Yeah, so that's the solution. That is the solution. So in terms of time complexity here, we will, because of these reversals here that we're performing, we will allow ourselves O of n, per O of n per array, per string that we're considering, on top of the recursive calls. So for solving a string of length n, we will use we'll perform operations on the order of n, and then on top of that, make up to 2 recursive calls to the problem. Although the sizes of the problems that we call will sum to n itself. So yeah, you can check that the complexity, it can be shown that the time complexity there will be O of n squared. So I won't go into that now. But yeah, that's the idea for the solution, and let me show you the code. Voila. So here's the code. It's quite short. So this is some input-output stuff as well. Just pretend it doesn't exist. In the contest, you just have to do input and output from files. So let's scroll down to main. And in the main function, all we're doing is, again, like I said, optimizing input-output, and then inputting the length of the string, the starting string, and the target string. And, well, I have a function called solve here, and then at the end I'm printing -1 because I haven't explained the format of the output, so you just have to print the moves you're performing with -1 at the end. And the moves you're performing, each move is just represented by the size of the prefix you're reversing. So this function here will print all the moves in the solution, and then I'll print -1 at the end. So what am I doing in the solution? So I'm taking the length, starting and target strings, and if the last character is the same, then I'm just pretending it doesn't exist, right? I'm solving one smaller. I'm just popping the last character from each string, and I'm solving the n-1 case if the last characters are the same, like we said. Of course, if they're the same and there's only one character, then we're done. Otherwise, so if the last characters are different, according to our proof down here, if the last characters are different, that must mean that there exists a prefix of the starting string, or of the current string, that is a suffix of the target string. Which means we can just go through, since we're allowing ourselves O of n time, on processing time on top of the recursive calls, we can just go through and find that prefix. So we have ones in the starting string and ones in the target string, and we're just counting them. So we're just going through, and we're adding up the values from left to right in the starting string, and from right to left. So the prefix of the starting string and the suffix of the target string. and we're doing that sequentially, one by one, until the number of ones is equal, which means the prefix of s and the suffix of t are anagrams. In which case, if we found this, now, like I said, so as we explained earlier, we will solve however big that prefix was. So this I represents the size of that prefix that matched the suffix. We will solve the problem recursively on that size. On that size, with the prefix of s and the reversed suffix of t. So we're taking the suffix of t and reversing it. Then, once we've solved that, we're printing n, because once we've solved to get this purple prefix to match this purple suffix reversed, then we need to perform this whole reversal of the whole string to actually get it in place to match the target suffix. And then that will bring this red suffix of the starting string to the front of the starting string, and then we will recursively call again to solve that. So yeah, so we've solved this subproblem, then we reverse the whole string, and then we take the remaining subproblem with n minus I digits, and we solve that recursively with the reversed starting string suffix. So that's it. And yeah, this assert, when enabled, it just checks that, this assert should never fail. If the assert does fail, then we have a contradiction in mathematics because we've proved that it should never be hit. We've proved that, this loop will never hit this I equals n condition. It'll never fail that because, because we've already checked this case. So if this assert fails, then maths is false. Maths is inconsistent. Or more likely, you've input strings that aren't actually correct, that aren't anagrams. So yeah, that's the solution. It's pretty simple. The code is pretty nice, and the proof is pretty nice. So I thought it was cool. So that's it for this solution. This was one of the intermediate problems in terms of difficulty at this year's bio final. So this, along with Frost and Fast, were the two problems that were sort of solved by 3 or 4 people, fully solved by 3 or 4 people. And then Cold War 1 was the problem that had the fewest solves. So I will link my solutions to the other problems to this contest as well in the description. So check that out. Yeah. Other than that, we are done. See ya.